Hello CSF, my name is Philip Haselwerter. Welcome to my talk about SSProve, a foundational framework for modular cryptographic proofs in COP. This is joint work with Carmine Abate, Exequiel Rivas, Antoine Van Muylder, Winterhalter, Catalin Hritcu, Kenji Maillard, and Bas Spitters. Before explaining what SSProve is, I'd like to spend a moment on motivation. Since their inception, game-playing proofs have been widely used both on paper and in formal methods. One concern for software engineering in general and in program verification in particular is scalability. Monolithic game-based proofs that reason about complex programs are very hard to verify. In SSProve, we build on the work of Brusca and his co-authors. In 2018, they crystallized ideas from the work on a large-scale proof effort for TLS into the method of state-separating proofs. State-separating proofs allow a modular style of verification by decomposing programs into packages. Composition of packages satisfies algebraic laws that can be exploited in high-level arguments. The SSP method is undoubtedly useful for pen and paper proofs, and we wanted to provide a way to combine existing techniques for computer-checked cryptography with the high-level SSP arguments. We formalized the state-separating proof methodology in the COG proof assistant. In the process, we had to give precise definitions for all aspects of SSP, including some that are usually left implicit. The theme of modularity figures at several levels in SSProve. The language supports modularity via packages, which are composed into programs, and our formalization of the logic and the semantics is obtained in stages, starting with a simple core and then transforming it to a more complex setting. To reap the benefits of this newfound modularity, we prove a theorem connecting high-level SSP arguments about packages to low-level program logic arguments about concrete code. We validated our approach by formalizing several examples in SSProve. In our CSF paper, we treat security of PRF-based encryption and El-Gamal encryption. Since submitting our CSF paper, we have also formalized security of a key and data encapsulation mechanism, and in collaboration with Nikolai Sidorenko of Sigma protocols. The ChemDem example was presented in the original paper on state-separating proofs, and during our formalization, we discovered a problematic corner case. We contacted the original SSP authors, and they promptly corrected the pen and paper proof that was previously published. Their updated proof has now been formally verified in SSProve. Let's get an overview of the requirements for our project before diving into the details of our approach. Consider an encryption scheme based on a pseudo-random function. Skipping over the definition of the key generation encryption and decryption algorithms, we ask ourselves, what goes into a security proof? There are two packages involved in the proof of security with respect to indistinguishability of chosen plaintext attacks. The package to the left, INCPA0, implements an encryption procedure, ENC, which takes a message as argument. This procedure first checks if the key has been initialized. If no key is available, it picks a key at random from a uniform distribution of bit strings of length n. It then calls the encryption algorithm based on the PRF with the key and the message as arguments, receiving the random seed R and the ciphertext C as a result. Finally, the encryption procedure returns RNC. The INCPA1 game implements a similar encryption procedure. It also starts with an initialization check for the key, but then samples a random message from a uniform distribution. This time the PRF encryption is called with the key and the random message, and we return the result. INCPA security is defined as follows. If we let an arbitrary adversary pick a message and call the encryption procedure with one of the two packages, the adversary will have a negligible chance to determine which of the two packages it was interfacing with. Before formalizing anything, we must choose a proof assistant, the system in which we want to express our formal definitions and proofs. We then have to define a core language to express our cryptographic code. It should support random sampling and manipulation of state, and we need to provide a formal semantics. We will need low-level reasoning principles that allow us to manipulate details of the code of the programs we compare, swapping lines, unfolding definitions, reasoning by case analysis, etc. We will define a probabilistic relational Hoare logic for this purpose. To achieve the decomposition of large programs into sizable pieces, we will define the high-level packages which are characteristic of the SSP approach to modularity. We are now ready to define formal games, adversaries, and security notions. Finally, we need high-level reasoning principles about composite packages to complement the low-level reasoning about code, and we need a bridge between the two worlds. So let's address these points in order. We formalized SSProve in the Coq proof assistant. Coq is based on type theory, a language that can express mathematical definitions and theorems, as well as executable algorithms. It has a rich ecosystem of libraries, both for computer science and for mathematics. Only the kernel of Coq has to be trusted, and it provides a tactic language for programming domain-specific automation. The encryption procedure of the NCPA0 package showcases all of the salient language features of our cryptographic language. Because we make memory manipulation explicit, the key initialization check has to dereference the memory location key to look up its value. In the same vein, if no key is found, the random value is first sampled as the local variable k and then stored at location key. The example code samples from the uniform distribution on bit strings of length n, but our language is flexible and supports other user-defined distributions. Imported procedures can be applied to arguments, and of course we can compose several computations in sequence. We also inherit pure constructs from Coq's built-in language, and this allows us to use ambient data types such as integers or booleans. So concretely, this language is defined in Coq as an inductive data type with constructors for each of the primitives. This allows us to conduct proofs by induction over the structure of code. And an advantage of small core language is that it is simpler to give the language a semantics. But nothing is lost by this frugality. We can define derived language constructs easily. For example, we can add an assert operator. If its argument evaluates to false, it samples from the null distribution that assigns probability mass 0 to its entire sample space. This corresponds intuitively to an abortion of the program, an operation that will never return a value. Another example comes from for loops, which can simply be defined by structural recursion. Today, I want to talk about the relational programming logic that we use to prove equivalences of code and memory invariants like equality and synchronization of initialization. But the final logic is similar to what you know from, say, EasyCrypt. But you can find out more about our novel modular semantics by watching the video recording of Antoine Van Muylder's presentation at Types 2021. So packages are the central notion of state-separating proofs. A package is simply a collection of procedure implementations that may read from and write to a common shared piece of state. The NCPA package implements one procedure for encryption and manipulates a single memory location key. An interface for a package describes the procedures it has to implement, the imported procedures it may call, and which part of the state it can manipulate. Two packages, P1 and P2, can be sequentially composed if all of the imports of P1 are exported by P2. Our definition of composition is more permissive than the definition given in the original SSP paper, in that it does not require packages to have disjoint states a priori. This allows us to avoid certain formalization artifacts, such as introducing a composition with a state proxy package when shared state is desired. Furthermore, packages can be composed in parallel by taking the union of their implementations. The original SSP paper stipulated certain algebraic laws that packages should satisfy, such as associativity or commutativity of parallel composition. As it turns out, these laws still hold in full generality with our definition of composition that allows shared state across packages. These laws form the basis for high-level reasoning about composite programs. The notions of games, adversaries, and indistinguishability can be defined without surprises. We consider security for closed packages that perform no calls to unknown imported code. And an adversary is a package importing the procedures implemented by a game G and exporting a run procedure. This time it is crucial that the only way in which the adversary interacts with G is by calling its exported procedures. In particular, the adversary cannot directly inspect the state of G. The advantage of an adversary is then defined as its chance of returning true more often when linked with G0 than when linked with G1. Two games are perfectly indistinguishable if that chance is 0 for all adversaries. With these notions in hand, we turn to the theorems that allow us to exploit SSP reasoning. The triangle inequality for advantages allows us to bound the advantage of an adversary against games F and H by taking an intermediate step via G. This is often useful because it allows further decomposition of packages into smaller or previously known configurations. The reduction theorem allows us to push equal parts of larger composite packages into the adversary, allowing us again to proceed working on smaller packages. This is possible only when M does not share state with G0 and G1. The SSProve methodology hinges crucially on the possibility to switch between high-level and low-level proofs when appropriate. This switch is enabled by the third theorem. It allows us to establish perfect indistinguishability of packages containing code that is not syntactically equal by proving in the relational logic that all implemented procedures are equivalent and that the state satisfies a suitable invariant. This concludes my presentation of SSProve, a foundational framework for modular crypto proofs in COC. And please check out our website, and thank you for your attention.